Hi, my name is Andrew Heimerman from Stacks, and today's webinar is about industrial robotics and industrial connectivity, and how we can simplify data aggregation and remote provisioning from robots that are located in industrial environments after they're sold to the end customers. So the global industrial and logistics robotics industry is projected to grow to a total of $415 billion by 2032. This is a 15% approximately year-over-year growth, which is driven by many factors, but one of the largest is the growth in e-commerce. Now we can imagine because of COVID, more people are buying things online, which means that there are more automated processes that need to come into play in industrial settings and for warehouses to be able to fulfill orders and returns on products. This means that more robots are being deployed in these environments, and with the trend towards Industry 4.0, more and more companies are going to need to implement robots in their systems or in their industrial environments in order to stay relevant and competitive. This means that there's also a growing number of startups and other robotics manufacturers who are creating robots to deploy in these environments, but who have issues connecting to them once they are deployed in their customers' environments. Namely, how do you get telemetry information? How do you control the software that's deployed there if you need to do pushing software updates, etc. And this is a major problem which is causing issues with scalability. But we'll get to that in a little bit. But first, before we go into the scalability issues with the world of robotics, it's important that we know what types of robots there are in industrial settings. So the first robot type is autonomous mobile robots, or mobile industrial robots, AMR and MIR for short. These robots have intelligent navigation. They can run autonomously. They do not require input necessarily from any users to interact with the world around them. And they construct a virtual map, let's say, of the warehouse or factory environment to navigate and perform tasks. Now, these tasks could be anything from retrieving goods from storage, or preparing things for shipment, or moving things down different manufacturing lines. There's many different things that these robots can do, and they act in an autonomous way. Now, the second type of robot is an automated guided vehicle, or AGV for short. Now, these are a little bit dumber than the last ones in the sense that they have fixed routes and have manual controls that are, or minimal programs that they follow in order to perform tasks in a factory. Now, these are very common because they're simpler to make. They require a little bit less connectivity than the autonomous mobile robots. And they have more predictable. They're simpler to predict the behavior, let's say, because autonomous robots have to make decision making. There's a lot more that goes into understanding the world than following a fixed route in the factory. Now, there's still a lot of these robots out there, and they also still need to be connected to the internet so that there can be, again, telemetry data, or let's say pushing new pieces of software to those robots, so that they can be kept up to date and maintain a longer life cycle. And now the last component in the world of industrial robots is predictive maintenance. Now, because these robots are hard to connect to currently, there's incomplete data sets and telemetry information that is not being able to be gathered from the robots when they're in the field after they leave the robotics manufacturer's let's say manufacturer. And so the services and data analytics require large data sets that are more complete, that provide a larger overview of how this robot is performing. So even things like where this autonomous mobile robot has gone, or what's the sensor health, or what sensors have they seen? Because there's also robots that are autonomous that perform predictive maintenance tasks, such as reading gauges that are on traditional machines that can't be digitized, and all this information is being gathered, let's say, in the industrial environment, but is not able to be shipped up to cloud service or any type of data analytics service to be processed to do predictive maintenance or analytics of how your systems are performing. So those are the three critical components to the industrial robotics field that we should know before going into a little bit further about these connectivity issues that I mentioned already. And this isn't just an issue for some of the companies. 75% of industrial IoT companies experienced issues with connectivity when they're rolling out the devices into customers' plants. This is due to restrictive firewall policies, let's say, or they have to set up complex VPNs, or they have to do some type of hacky solution in order to get internet connectivity to their devices. Because again, once they give them over to the customer, they have very little control about what type of IT environment they're in. And especially with industrial environments where you have a kind of a blend between the operational technology in the machines that's been developing and the IT that's been developed over the same period of time, they developed in parallel. So there's protocols for the machinery, there's protocols for the internet. Getting them all to come and play nicely together is also a problem in general. And there's a lot of different things that you have to have for IT in one of these industrial environments that makes it difficult, or at least a lot more complicated to implement a good connection to your robots. That is also secure, I should add. Exactly. So kind of what I already mentioned, the showstoppers for industrial networks are security issues. Obviously, industrial systems are vulnerable to attack because they provide critical services. And due to older technology in these in some of the industrial facilities, the level that is the level of the security that's in the IT infrastructure there already could be more restrictive than compared to the latest and greatest in IT. So I mean, if you're working purely with cloud solutions, you're always getting the newest updates. With manufacturing solutions, these updates are not so frequent, and because of the nature of the industry, because you're dealing with heavy machinery, etc., they don't come as frequently. Additionally, there's weak network performance. As you can imagine, if you're trying to spread an industrial Wi-Fi network throughout a bunch of metal machines and over a large area, there's going to be connection issues in general, which means there's unstable connection for these robots to get to the IT in the factory itself, let alone to cloud services or solutions that you may have outside of the factory network. And of course, because of all these issues, implementing and integrating systems becomes quite a costly experience. You have to really do a lot of synchronizations with the IT of the factory, with your IT as a robotics manufacturer. It can cost a lot of money. It definitely costs a lot of time, and it becomes a problem for getting, not only for the robotics manufacturers themselves for connecting to their devices, but it makes it more costly for the end customers of these robots as well. It's one of the larger impediments to the industry. The cost. I mean. Especially for small and medium-sized enterprises who can't afford to build out one large all-in-one system, or spend a ton of money to revamp their whole factory floor. They need smaller, faster solutions that cost less, but still provide the same level of output. And so that's what we're trying to do by creating, if we were to remove these connection barriers to the robots. And to go into the showstoppers of IoT networks in the numbers, there's massive security issues, obviously. 4.24 million is spent on average per company for data breaches. That's not a small number, and if you have critical information on your networks, especially in manufacturing, this can be absolutely devastating, and probably even higher of a number for damage. And like I mentioned before, weak performance, high latency, and dropped connections prevent a high data throughput for IoT networks. And that's obviously not something good for robotics, especially autonomous robots, which need to have up-to-date information, especially when they're communicating with other robots or other machines, people interacting with other machines. You can't have high latency when you're trying to make autonomous decisions in a moving environment in a factory. Which could lead to not only just physical damage, but injury of workers and much more. And then to bring it back into what I was talking about before, the average integration I'm sorry, the integration spend globally is about $389 billion a year. So this is not a low number. This is definitely a showstopper for smaller companies who are trying to implement new technologies for Industry 4.0. So what are the problems for industrial robotics companies? They don't have physical access, like I mentioned before. Once you give off your device to the end customer, you don't have control over. You can't just waltz in and plug into the robot and make changes all the time. You'd have to go through the company, et cetera, et cetera. There's also then no two-way connectivity to devices because oftentimes these industrial networks want to close off most contact with the outside world. You don't have the ability to send and receive information very easily from the robots or to the robots from your cloud services or data services that you have running on your own infrastructure as a robotics manufacturer. Additionally, the robots can't communicate with each other. There are difficulties in linking up larger than local networks. So I'm going to get to this a little bit later, but there's an operating system called ROS for robotics, and there is a networking agent inside of there, but it's mostly focused on local clusters of robots. This doesn't really extend when you get out to what happens if you have multiple different factories or you have a fleet that's operating over a large area which doesn't have some type of local network capabilities. These robots then can't really communicate with each other, which means that there's no way of actually getting some type of swarm intelligence or interaction on on a larger scale besides just each individual robot operating on its own autonomous information. Additionally, like I mentioned, created data cannot be simply integrated with cloud data services. This goes back to the no two-way connectivity. And there are lossy wireless conditions, and each new customer requires new network configurations. Because like I mentioned before, the IT is independent or is unique for each different case or each different factory, each different warehouse based on the needs of that particular company. So these are major issues for scaling out industrial robots, especially with the last bullet there, where each new customer to bring in requires a lot of integration time. So one of the ways that works that a lot of companies are working today is using VPNs, but this is a suboptimal solution for a few different reasons. The first reason is each factory requires then its own. Or like each end customer, let's say, requires its own VPN server. It's all the configurations have to be set up. You have to set it up on their company process premise. You have to make sure all the firewalls are in order so that your VPN connections can go through. You have to make sure that all of the robots are provisioned for that VPN with that VPN key. And then imagine having to do this over every single new customer that you do, or every single new environment where you're deploying your robots. It's not very scalable, and it's clumsy, and VPNs are notoriously tricky to set up. Another solution would be SSH reverse proxies. Again, another issue with having and something I forgot to mention here before. VPNs provide they become then a central point of failure for your networks. If someone took down the VPN server, or then you lose all connectivity to your robots. They lose connectivity to the services that they're trying to access. Like, for example, if they're trying to get information from your cloud or from other robots, it won't work. So it's actually just it's another security risk for the deployment in general. Exactly. So back to SSH reverse proxies. So this is another non-scalable solution because each running service, so each program that's running on the robot that you need to connect to or have connection to the outside world, must be manually configured for each one. So that means, if you have one service doing this, that's one one connection that has to be maintained. If you have another service doing something else, like let's say it's sending telemetric data, you'd have to configure that one as well to have a specific port and make sure that it's all properly set up on both ends, not on the server, on the end destination, so like your cloud, and on the robot itself. Or if you use a proxy server, that's another centralized. It's another centralized component that can be taken down. Additionally, SSH performs poorly in lossy and unstable networks. If you lose connection, if you lose an SSH tunnel, then you have to reconnect it. You have to restart it, and that is a manual process that you don't want to have to do, or you have to write a script to do for you. And exactly, there's a lack of auto reconnect. Yes, exactly. Actually, a great example of this is there is a shell called Mesh, which actually is, in order to deal with the SSH lack of auto connect, was specifically built to handle this problem with dropped SSH. So it's not a first time that people have realized that this is that with lossy networks, or when you're roaming, especially if a robot's connected over mobile networks, there's a high chance that you're going to lose your SSH connection. So it doesn't work in a scalable way, and so that's not optimal for each robotics company to maintain. And I guess then the other question is, if the robots are autonomous or guided, why connect them at all together? And this goes back to just the principle of why connectivity is important, because industrial robotic connectivity adds value. It brings smarter predictive maintenance, because you can actually access the data that your robots are producing. You can get a better view of what's going on in the environment, how they're running. You can even get information, like I mentioned before, from gauges if you have an autonomous robot that's doing predictive maintenance for heavy machinery. All of this is a value add when you're able to connect to the robot. Additionally, over-the-air software upgrades, so pushing new software to your robots, finding bug fixes. It not only makes the lifetime of the robot longer, it adds more security over time. It means that you can add new features, and which is also for your end customer, for a robotics manufacturer's end customer, more value in long term, because that means that they could even buy new packages. So like if you need new functionality for a robot, you could buy that package from, or that company could buy the package and implement it onto their robot, and automatically gain real tangible value in their industrial environments. And lastly, multi-robot swarm intelligence is another value add that connectivity provides. If you can extend the worldview of each robot that's running autonomously by collecting the information, or collecting sensor information and telemetric information and application information from other robots that are in the same fleet, you can create each one of the robots can actually have a larger input of data and a better worldview of what's going on in its working environment, which can lead to higher performance, better efficiency, better safety for employees in the factory or warehouse as well. So robotic connectivity is the future, and it brings more value, and that's why leaving them as dumb robots that just follow simple tasks is not the way forward. Now, we have all these issues today, but how do we solve them? So now I'm going to present a solution that we've created here at Stacks to help solve the networking and orchestration issues for robotics in industrial environments. So just an overview of what Stacks is. It is it's two lightweight agents that are deployed on any IoT device, any cloud service, or on-premise machine. These agents then make a peer-to-peer network to share data and services, and create global identifiers for each node, so each item or each node, each robot, for example, and the processes that are running on it, so the data services. Then the network of connected agents and their applications are orchestrated with a decentralized provisioning, deployment, and monitoring tool, and it's all securely encrypted from between different nodes in the Stacks network. So with Stacks on a robot, what does it actually offer these robots? Because it's a peer-to-peer network, it has built-in redundancy and ensures that there's connectivity to devices and services, even in lossy environments. It's like industrial environments. It can be up to 5 times faster than TCP, which is faster and less complicated than VPN setups, and still provides connectivity across different network barriers. So with Stacks, not only is it a peer-to-peer network within the industrial environment, but you can link up your cloud and your robots that are located in completely different networks and environments behind NATs and behind firewalls, and you still maintain all this connection and this connectivity while keeping a very high throughput and low latency. And it also brings in a higher level of scalability. Stacks is a plug-and-play network where if a robot goes on or offline, the network doesn't need to be reconfigured. It means that if you're adding new robots to your fleet, you just have to simply turn them on and connect to any of the existing nodes that's already there, which saves time and money and makes integrations a lot simpler. So we can reduce the cost that it takes for robotics companies and their customers to integrate their systems together. So I talked a little bit before about the robotic operating system, ROS, and Stacks, and here are some of the comparisons and the differences between the two solutions. So ROS, it's a little bit older. It's been on the market since 2007, but it provides a lot of very interesting support for hardware drivers and for building the robots themselves and making them function. So it's truly like an operating system. However, the networking middleware called DDS is based on PubSub, which is distributed but still centralized. So the same with VPNs. It means that there is a centralized point of attack that could happen, and if it goes down even just for benign reasons like the power outage or something like this, you lose the ability to connect to and receive information from other services or robots. It also is optimized for single entity management, meaning you can't have a consortium of different partners. So like let's say the robotics manufacturer and the industrial customer want to work and interact with it together and manage it together from an IT perspective. It's difficult to do. And so it's not optimized for that. Additionally, the networking is mostly mostly used for local networks. So like over a local Wi-Fi network, you can connect the robots, but it's not really built for larger scale distributed systems. And what Stacks offers in comparison is almost zero configuration setup. Simply you start it and you point to an existing boot node, which can be located anywhere in the cloud or on premise. As long as it is available publicly, you can use it. And that allows then hot swapping and a fully decentralized fault tolerance. So no matter what, exactly like what I said before, no matter if you have peers coming in and off, or if you're adding new robots, whatever, you do not have to worry about having to reconfigure the network or losing the network if some of them fall off. Stacks is also built for any system, including legacy services. ROS is really focused on just robots, but that kind of, in the real world, when you're building a larger system, when you have services in the cloud and you have data services on hardware, like physical hardware, physical servers, other computers, you name it, you need a more robust solution that can handle all those different types of devices. Stacks also offers software-defined networking, so you can section off different things. Like let's say you have one environment in one factory and in another, and you want to separate them out. You could have the same Stacks network, but have functionally separated sections of the network using software-defined networking techniques. Stacks is also extremely scalable across different physical networks. Like I mentioned before, you can have a Stacks node in any network or infrastructure, no matter where it is globally, and it will still be able to connect and work properly. Additionally, it also has service multiplexing, so something that like I mentioned before, that SSH doesn't have. So you can have multiple applications that flow all of their data through one single port. So Stacks actually only needs one singular port to function, which actually makes it a lot easier for integration for the security teams. They really only need to allow one outgoing UDP port, and then we can establish connection in a two-way manner between any nodes. That makes it a lot easier for maintenance, and especially when you just have to deal with one port versus however many for a solution, you can obviously see that is going to be a major reduction in time and efforts from the IT side. Also, like I mentioned before, Stacks is performant in lossy networks, and we provide container orchestration on top of the peer-to-peer network without any centralized service. So it's different than Kubernetes in that there's no master worker concept. So here's an example of what a Stacks-enabled infrastructure could look like. So on the left, you have the factory infrastructure where you have robots on the side here. And then you have the robot manufacturer here on the right in their infrastructure. So their data services, their cloud services. In the middle, we have a shared pool of predictive maintenance. So you hear closer to the edge, you've got maybe a couple nodes that are doing some things. It may be the robotic manufacturer has some more let's say like hardcore, more technical or more, let's say computationally heavy processing that happens over here in their infrastructure. And they can be linked over any type of network boundary. So firewall here, you still maintain all the connections to the different nodes. Any node can talk to any other, and it kind of makes for a larger mesh network that for developers, it looks like as if it's all just one environment, which is handy. Oh, and I should mention that this is Stacks also supports this collaborative approach. So yeah, so this doesn't have to be just like this could be any piece of software if you wanted to have it running in both infrastructures and both parties are also contributing to it. I don't know. That is also possible. Each party can upload their recipes for their containerized software, and then the other party can then deploy it on top of this network. So there's a lot of different things, and you can go into it very deeply, but I won't do that today. You can say that for actually, if you want to reach out to me, I can go deeper into that, or we can save that for another webinar. But yes, so anyways, all this infrastructure becomes available and interconnected simply, two-way, and with minimal hassle. And here's just some protocol comparisons, just to put some numbers behind what I was talking about before for speed and overhead. As you can see, the Stacks protocol is actually slightly smaller in overhead for the message size compared to TCP native. A little bit more overhead for the ACK messages, but if we compare to OpenVPN or WireGuard, we are highly performant and doing and pushing through a lot of data for without a lot of waste. So that's all I have for you today. If you have any questions, please feel free to reach out to either Alexandra or myself. We're happy to answer them. We have our software available online, so you can sign up for a free month trial at our website. And our documentation is also available online at docs.stacks.io. And yes, so again, please feel free to reach out to us if you have any questions, if you'd like to go in deeper, if you have any comments. So thank you for listening and have a great day.